Maxima and minima. This is not an astronomy video. I'm making this for my Year 2 BTEC Maths for Construction students because they asked me to do it. They've got an exam on Monday. Anyway, maxima and minima, practical examples. First one, a ball is thrown into the air. This equation gives its height as a function of time. Calculate the maximum height reached by the ball. So h equals 2 plus 12t minus 5t squared. So the maximum height, let's differentiate it and find dh dt. So dh dt is 12 minus 10t. If it's a maxima or a minima, then this will equal 0. So 12 minus 10t equals 0. For the max, this is 0. So 12 equals 10t. So t equals 1.2 seconds. Then if we substitute this value of t in the original equation, we can find the maximum height, which works out at 9.2 meters. Note that the second derivative, d2h dt squared, would be minus 10, and that tells me that it's a maximum because it's negative. This one's a little bit trickier. A box with a square base has no top. If 64 centimeters squared of material is used, what is the maximum possible volume for the box? Now, I would start with a diagram to get it into my head what's going on. We have a box with a square base. I'll call the bottom x by x, and we'll say the height of the box is h. And then I'm going to get an expression for the volume in terms of x. So an expression for the volume in terms of x. So the volume is x squared times h. I want to get rid of h though, so I've got some more information. I know that 4hx, which is the area of one side, plus x squared equals 64. So rearranging that, I've got an expression for h in terms of x, and then I can then put that in the first equation, and I have the volume in terms of x. So v equals 16x minus x cubed over 4. If I differentiate that, dv dx is 16 minus 3x squared over 4. And if I put that equal to 0, that will tell me the value of x, where the volume is a maximum. And that works out at 4.62. If I put that value of x into one of the equations above, then that will give me the value of h, and then if I know both of those, I can work out the maximum volume. Again, note that the second derivative is negative. The second derivative is negative, so this is a maximum. One more example. A rectangular lot is bounded at the back by a river. No fence is needed along the river, and there is to be a 5-meter opening in front. If the fence along the front costs £1.50 per metre, along the sides £1 per metre, find the dimensions of the largest lot which can be thus fenced in for £300. So again, a diagram. If you haven't got a diagram, draw a diagram. There's the river, there's my rectangular plot. I'm going to call that distance x, and we have y and y, and then at the front we've got x minus 5. The information that we're given, we're told 2 times y plus 1.5 in brackets x minus 5 equals 300. Look at the information we're given, you'll see where that equation comes from, and then the area is x times y. So again, what we want is the area just in terms of one of these variables. So what's the area in terms of x? So rearrange the equation for y and then get rid of y, sub it in. So I've played around with it. I've got the equation in terms of y. I've ended up with y is 153.8 minus 0.75x. And so the area is that times x. So the area is that. Differentiate it. So dA dx is that. And for the maximum, I put that equal to 0. And we get a value of x of 102.5. Once we have a value of x, then we can work out a value of y, and we can work out the maximum area. And again, the second derivative, if we differentiate it again, we get minus 1.5. So the second derivative is negative, so that will be a maximum. So study those 3 examples. If you can do them, then you can do the ones which will be on my test, and that's that.